Hi everyone, Jun Rao from Confluent. In this module, we're going to talk about how Kafka replicates its data in the data plane. Earlier, I mentioned that within a Kafka cluster, we have this control plane and a data plane. And in this particular case, we're going to talk about how the data plane handles data replication. Replication is a pretty critical feature within Kafka. It's a critical feature to enable higher durability and availability, and it's used for build mission-critical applications on top of Kafka. Enabling replication is actually pretty easy. So when you create a topic, you can specify how many replicas you want to have. Once you specify the number, then all the partitions within that topic will be created with that number of replicas. If you create a replication factor with n, in general, we can tolerate n-1 failures. Here are a few key concepts with replication. Once you have created those replicas, one of the replicas will be designated as the leader of that partition, and the rest of the replicas are called followers. The producer will be first sending this data to the leader, and from there, all the followers will be retrieving the data from the leader. And the consumer typically reads data from the leader, but as we'll see later on, it can be configured to consume data from the follower as well. Another key concept in Kafka is called in-sync replicas, or ISR. Intuitively, ISR is a set of data that captures all the replicas that have fully caught up with the leader. In the normal case, when all the replicas are live and are healthy, all the replicas will be part of ISR, or these in-sync replicas. Each of the leader is also associated with a leader epoch. So this is actually a unique number that's monotonically increasing, and it's used to capture the generation or lifetime of a particular leader. So every time when the leader takes the data from the producer request to write to its local log, it needs to tag all the records of this batch with its leader epoch. As we'll see later on, this leader epoch is pretty critical and important for doing log reconciliation among all the replicas. So once the leader has appended the produced data into its local log, all the followers will be trying to retrieve the new data from the leader. The follower does that by issuing a fetch request to the leader, including the offset from which it needs to fetch data. After the leader receives this data request, the leader will be returning the new records from that particular offset to the follower. Once the follower receives a response, it will be appending those new records in its own local log. As you can see, as the follower is appending the data to its local log, it keeps the same leader epoch included in those record batches. We need a way to commit the offsets, meaning that those records have been considered safe. In Kafka, the way we commit those records is defined by once a particular record is included in all the in-sync replicas, then the record is considered committed and then can be safely returned to the consumer. So now, how does the leader know whether a particular follower has received a particular record? This is actually piggybacked on the fetch request from the follower. So by sending a fetch request from a particular offset, in this case offset 3, the leader knows that the follower has received all the records up to offset 3. And in this case, if both followers are doing the same thing of issuing fetch requests at offset 3, then the leader will know that all the records 0, 1, 2 have been received by all the replicas in this in-sync replica set, and those records can be considered as committed. The way we modeled committed records is through this concept called high watermark. It marks the offset before which all the records are considered as committed. In this case, will be advanced the high watermark on the leader to offset 3 after the fetch requests have gone through at offset 3. All the records up to the high watermark are exposed to the consumer. Once the leader has advanced the high watermark, it will also need to propagate this information to the followers. This is done by piggybacking in the fetch response. As you can see here, in the fetch response, the leader will also include the latest high watermark to the follower. As you can see, since this is done asynchronously, the follower's high watermark typically is a little bit behind of the true high watermark in the leader. Now, let's talk about how we handle the leader failure. Let's say in this case, the old leader broker 101 has failed. We need a way to elect the new leader. The leader election in Kafka for the data plane is pretty simple because through the protocol, we know all the replicas that's in ISR, all those in-sync replicas, have all the previously committed records. So we can pick any of those replicas in ISR as the new leader. In this case, both controller 102 and 103 can be the new leader. Let's say we picked 103 as the new leader. This information will be propagated through the control plane. Once replica 103 notices that it's the new leader, it can start taking new requests from the producer. As you can see, for the new produced request, it'll be tagged with a new bumped up leader epoch, which is 2. If you are careful, you will notice there's a subtle issue with the high watermark once a new leader is elected. As you can see, the high watermark in this new leader is actually less than the true high watermark in the previous leader. Now, what happens if a consumer is issuing a fetch request in this time window asking for offsets in the middle, let's say offset 1. In this case, we don't want to send a response to give the consumer the wrong indication its request invalid because this is a transient and a temporary. So instead, what we do is we'll be issuing a retryable error back to the consumer client so that it can keep retrying until this high watermark catches up to the true high watermark. This should be done pretty quickly. Once a new leader is elected, some of the followers may need to reconcile its data with the new leader. As you can see in this case, the follower on broker 102, it actually has some data in offset 3 and 4. Those are actually the records are never committed, and you can see they are actually quite different from the corresponding records in the new leader. So we need to have a way to clean those records. This is done through the replication reconciliation logic. The way we do that is through another detail in the fetch request. When the follower is issuing fetch request, in addition to the offset from which it wants fetch data, it also includes the latest epoch it has seen in its local log. In this case, it's epoch 1. Once the leader received the fetch request, it will use the epoch information to check the consistency with its local log. In this case, it realized that within its local log, epoch 1 really ends at offset 2 instead of offset 4 indicated by the follower. So the leader will send a response indicating to the follower that you really need to make the log consistent with respect epoch 1. In this case, it will tell epoch 1 really ends before offset 3. When the follower received this fetch response from the leader, it will know it needs to truncate the data at offset 3 and 4, and at this point, the data is consistent with the leader up to offset 2. Next, the follower will issue an next fetch request starting with offset 3 with the last epoch 1. Once the leader received it, it noticed this is actually consistent with its local log, and this will cause its local high watermark to be advanced to offset 3. Next, the leader will be returning new data back to the follower, and the follower will take this data and then appending that to its local log. Then the follower will fetch again with latest offset at the offset 7. This will cause the high watermark in the leader to be advanced to offset 7. Now, this completes the reconciliation between the follower log and the leader's log. Now you can see they are identical. At this point, we are still in this under-replicated mode because not all the replicas are in ISR. At some point, this failed replica on broker 101 will come back and it will catch up from the leader and will go through a similar reconciliation logic as replica 102, and eventually it will catch up all the way to the end of the log, and then it will be added back to ISR. Now we are back into the fully replicated mode. Now let's take a look at how follower failure is handled. And sometimes a follower can fail, or sometimes maybe a follower is just slow. It can't catch up with leader. In this case, if we keep waiting for that follower, then we'll never be able to advance the high watermark. So what we do instead is the leader will keep monitoring the progress of the follower. It will measure what's the last time this particular follower has caught up all the way with the leader. And if it's lagging by more than a configured amount of time based on this property, then this follower is considered out of sync. Then it will be dropped out of ISR. At that point, the leader can now advance the high watermark based on the reduced in-sync replica set. This is how we handle the follower failure. The last thing I want to talk about is balancing the load of the leaders. As you can see, the leader replica typically does a little bit more work than the followers because all the followers are fetching data directly from the leader. So in a healthy cluster, we want the load on all the leaders to be balanced. This is achieved through a concept called preferred replica. So when you create a topic, we'll designate the first replica of each of the partition as the preferred replica. So when we assign the preferred replica, we try to assign in such a way the preferred replica will be distributed evenly among all those brokers. So when doing the leader election, what we try to do is to periodically look at to see if the preferred replica is healthy and then whether the current leader is on the preferred one. If not, we'll try to move the leader back to the preferred replica. So in the end, all the leaders will be moved onto the preferred replica, and since these are evenly distributed among all the brokers, we can achieve balanced load among the leaders in the cluster as well. Yeah, this is the end of this module, and thanks for listening.